Let's see, this may be a good time to start. Harry, what do you think? Okay, so welcome everyone. We are resuming our quantum colloquium for this fall. So it's a great pleasure to have Harry Zhou here from QuEra. Harry has had quite a excursion through physics land. He started, I think, as an experimentalist working on diamond spin centers, both at MIT and then at Harvard. But he soon found his calling in Misha Lukin's group, working on neutral atom arrays and specifically on architectures for error correction and fault-tolerant architectures. And he's been deeply involved in their work. This is really beautiful work. Today he's going to tell us about the latest installment of this. I think this should be a really great talk. I believe Harry has spent a lot of time trying to make his talk really accessible to this very broad audience here. So, Harry, looking forward to it.
Yeah, thank you, Umesh. Let me share my slides. Can you see it?
Yes.
Great. Yeah, thank you, Umesh, for the very kind introduction. And it's a great pleasure to have the opportunity to speak at the Simons Quantum Colloquium, which I have attended many times in the past. So today I'm excited to tell you about some of our recent work on transversal algorithmic fault tolerance for low overhead quantum computing. So in the past few years, we've seen a lot of exciting progress on early quantum computing systems, with many different experimental platforms all making fantastic progress and starting to see some early algorithm implementations of various kinds. But of course, we would like to see how we can really take these ideas and extend them to large-scale quantum computation. Now, in thinking about the large-scale quantum computation, one of the most glaring issues that we see is error rates. For example, the physical error rates that we have today on the order of 10 to the minus 2 to 10 to the minus 3 are very far away from what is generally believed to be required for large-scale algorithms, such as Shor's algorithm or large fault-tolerant chemistry calculations on the order of maybe 10 to the minus 12 to 15. And so really, as we think about large-scale quantum computation, fighting decoherence and errors is really the central challenge if we want to take the promise of quantum computing to this full scale and make it happen. Now, fortunately, a lot of great work has been done in the community in the form of quantum error correction, which really gives us tools to be able to bridge this massive gap between the physical error rates that we have today and what is required at large scale, as long as we can go below the threshold and if we provide enough resources to perform error correction. So what does error correction, or more generally fault tolerance, do? Well, the idea is that if we had just had a single physical qubit, then a single error might just directly corrupt the quantum information, so that would be pretty bad. But by encoding the logical information, or our qubit, into a logical qubit that is delocalized across many physical qubits, now things are likely okay as long as we don't have too many errors in the system. And indeed, fault tolerance offers us a deep lens into thinking about the physics of quantum information here. It tells us how we should protect quantum information in a robust way and how we can structure the qubit to really be insensitive to all of the different types of errors that might occur in our system. At the same time, it's important to remember that ultimately we're not just interested in having qubits, we're interested in really doing a computation with it, doing something interesting in the form of a computation that might be classically intractable. And so a very natural question to ask is, instead of thinking about fault tolerance of individual qubits, is there anything that we can gain by instead thinking about the fault tolerance for the algorithm as a whole, thinking about the whole procedure and asking the same questions of fault tolerance? And moreover, if we take this point of view, are there consequences that we might have in terms of the cost of computation, such that we might be able to do our large-scale computations maybe a little bit more cheaply than we previously may have thought? So indeed, when thinking about the cost of large-scale quantum computation, it really is quite daunting. For example, for the neutral atom systems that we work with, where we maybe have on the order of 100 microsecond gate due to the atom moving, as well as 100 microsecond measurement time. These nice estimates, this particular one was performed by Madelyn et al. From Microsoft. These large estimates suggest that the computations that we need to do will take almost a year if you look at the vertical axis of what these parameters would correspond to. So that's really long, definitely not something that any grad student would want to be running. And a large part of the reason why it's so slow is because the logical clock speed is typically much slower than the physical clock speed of the system. So in particular, in many constructions, for example, the standard surface code plus lattice surgery, we typically have a logical clock speed that is slower by a factor of d being the code distance, and usually scaling logarithmically with the total space-time volume of the computation so that you have enough suppression given the exponential error suppression to make sure that no error occurs throughout the whole computation. Typically, this d is around on the order of 30. So right out of the gate, we get a factor of 30 slowdown of executing a logical computation compared to our physical operation speeds, which are already on the slower side if you compare to classical computers. And so what I'll be telling you today is methods that potentially can reduce this from this almost a year level timescale down to a few days, even with these relatively slow physical hardware parameters. And the key idea is that by considering the fault tolerance of the entire computation and focusing purely on the classical output, which is really, at the end of the day, us running the computation, what we as observers actually care about, by focusing on these minimal requirements, we actually come up with constructions that allow us to only do order 1 rounds of syndrome extraction instead of d rounds, thereby giving us a speed up in terms of the clock. In more detail, we developed a fault tolerance method that we called Transversal Algorithmic Fault Tolerance, which achieves an order d speed up relative to conventional fault tolerance methods, where again, d is the code distance characterizing the amount of error suppression. And translating into practical terms for our reconfigurable neutral atom array architectures, this translates into about a 10 to 100x speed up, depending on the parameters. Now, a few comments to make here. First of all, the technique really does reduce the overall space-time volume instead of trading, say, the time axis for the space axis. And so it really is reducing the overall cost of the computation. The magnitude of the saving on the order of 10 to 100x is actually comparable to a lot of the savings that we get from these sequence of really nice works on quantum LDPC codes, quantum low-density parity check codes, which are methods for encoding things in a way that is much more space efficient. So these really are complementary axes of improvement. And it may very well be that the savings that we get on each side might actually multiply. Finally, a very important point is that for our theoretical analysis, we have been assuming fast classical decoding, which is, of course, an important assumption that I'll come back to and discuss towards the end of my talk. Great. Great. So in today's talk, following this target, I'll give you first a brief introduction of common fault tolerance constructions. There are many kind of different forms, but the key idea of a lot of the formulation is to try to make individual logical operations fault tolerant, and then compose them in a way that makes sure that our whole computation is fault tolerant. With our approach, instead, we'll try to directly approach the whole computation and try to come up with ways of making the whole computation fault tolerant without requiring these individually fault tolerant building blocks. Of course, this doesn't come without some challenges, and so we'll describe what the conceptual challenges that maybe led people previously to overlook this possibility and how we resolve these challenges. And then finally, I'll show you how, with circuit level numerical simulations of this of these techniques, we see that the result is quite promising, where the threshold is almost the same as the standard schemes that people would employ with D rounds. So we'd like to make our quantum computation fault tolerant, and to do so, we start with the ideal quantum algorithm that we're trying to implement that involves maybe some gate operations, some measurements, feed forward. So the first step is, of course, we want to encode our qubits into logical qubits. And then we also want to replace our gate operations by logical gates. So a very simple one is the so-called transversal logical gate, where you take two code patches and then you just bring them together, do a physical C0 gate between each of the corresponding qubits, and this turns out to implement a logical C0 between these two encoded logical qubits. This particular form of transversal gate is really nice because, as you can see here, each physical qubit in a code patch doesn't talk to a different qubit within the same code patch. And so this actually helps us control the error propagation and makes it easier for the whole thing to be fault tolerant. Moreover, it's also directly acting on the logical information, which allows us to perform logical operations much more directly instead of using other techniques that might rely on intermediary degrees of freedom. And finally, another nice feature is that for the surface code or the color code, some of the commonly used error correcting codes, the Clifford group, which is kind of the nice and easy set of gates involving C0s or single qubit 90-degree rotations along axes, these gates can actually be implemented transversally. So a lot of the useful gates that we can have access to are also very naturally implemented. Of course, the Clifford group by itself is not universal, and we'll get into how we make the whole computation universal later on. So we've translated the gates, but we still need to make sure that we can detect and correct errors. And so to do so, we insert these so-called syndrome extraction rounds, which allow us to gain information about where errors may have occurred and allow us to go and correct these errors. And the game of fault tolerance is then to make sure that when we're thinking about all of these different things, where everything we have here is noisy, the gates are noisy, the syndrome measurements are noisy, we want to make sure that even after all of this, any kind of physical error is unlikely to corrupt our logical operation. In particular, we want the chance that our logical operation gets corrupted to be exponentially suppressed as we grow the code size so that it becomes very unlikely. Now, a common way to achieve this and analyze it is by combining gadgets that are individually fault tolerant. So for example, if we have our previous computation, then we might slice it into many different pieces. Some of them are doing state preparation, some doing gates, and we want to show that each individual one is fault tolerant. And then we want to be able to glue them together in a certain way such that we know that the whole computation is fault tolerant. To do so, a very natural way of allowing us to glue them together is to have an input-output contract for each of our blocks. So for example, we might impose that if we gave you a quantum state that's close to a logical code word as the input, then after you do your operations and do your logical gate, the output state remains close to a logical code word. In this way, if we can build this up in a step-by-step fashion, then we can glue all of our blocks together, and that will give us fault tolerance for the whole computation. So let's try to examine how easy or difficult it is to realize this contract of having a good close to code word intermediate quantum state. And for simplicity, let's just consider the simplest thing of just preparing the logical code state. So we're trying to prepare the logical zero state from a bunch of physical zero states that we're given. So a very natural way to do this might be to try to measure the syndromes. And now if we could measure the syndromes perfectly, then when we measure syndromes afterwards, we can apply a correction to reach back into the code space. And moreover, because the initial state that we started with was an eigenstate of the Z logical operator, and the syndromes that we're measuring commute with the logical information, this tells us that we should be able to go into the logical zero code word if we could measure syndromes perfectly. But of course, in reality, we can't. And so what can often happen is that if we only measure the syndromes, say order 1 times, then a single syndrome measurement error, for example, in the middle of the system, could actually cause a very large physical correction that causes us to be very far away from our logical code word. And so typically then, of course, there are some exceptions with certain specific families of codes that might have the single shot property. But in most cases, for a general code, what we do is we repeat this order d times in order to gain confidence about the syndromes we're measuring. And then after we apply the correction, we can make sure that we go to the 0 code state. Okay, so because the syndromes are noisy, we also need to repeat many times on the order of the protection of the rest of the system that we're hoping for, such that we can gain confidence and make sure that we're really reliably preparing this state. Now, suppose that we didn't do this reliable preparation and instead just tried to do it with order 1 rounds, where we just measure the syndrome once and we try to do something. What would go wrong there? Well, intuitively, one might expect that if the state preparation was not reliable, then there could be initialization errors, which ultimately then might lead to incorrect logical measurements. We're then using these logical measurement results to apply a feed-forward operation. So an incorrect logical measurement might very well lead to an incorrect feed-forward gate. And then we might continue with our circuit, doing some more Clifford gates, possibly more measurements, and we'll gain some more syndrome information around here. Now, later on, we may have realized that we made a mistake earlier, but we've already done many gates, and it might be very costly to try to reverse these gates, let alone maybe possibly even measurements. And so this might seem like a major problem, and indeed, this I think was one of the major reasons why in a lot of analyses, in one form or another, it was assumed that our state preparation and our measurement need to be separated by d rounds of error correction. So just to summarize again, this common approach, we're trying to guarantee that we have individually fault-tolerant operations. And what that typically involves then is to have a contract so that when we go from one block to another block, we can connect these different building blocks together. A common way then to achieve this connection is by guaranteeing certain properties of the intermediate quantum state that we have. But as we saw generically, if we want to guarantee the quantum state that we have, this might require on the order of d rounds of syndrome extraction in order to be confident that we're putting things back close to the code space. So in our approach, we're going to try to examine these assumptions that are being made when we analyze the fault tolerance and to see if we can actually do a little bit better. So in particular, instead of considering just the individual operations, we'll try to consider the whole algorithm. So now we're no longer requiring that each individual operation is fault tolerant. We just want the whole computation to give us the right result when you do the whole thing. Moreover, when considering the whole thing, really we're only interested in the classical output of the computation, because ultimately, whether we're trying to estimate the ground state energy or trying to factor a number, we're interested in the classical bits that we ultimately get out of the quantum computer. And so we're only going to try to guarantee the classical output without forcing a guarantee on the intermediate quantum state. And it will turn out that with this, actually, we can get away with order 1 rounds per operation instead of the order d rounds that we already saw for the state preparation problem. Now, of course, it might not be obvious to you if we're not guaranteeing the quantum state, how are we even getting the correct output at all? And to do so, we'll need to utilize the microscopic understanding of these initialization errors that we were worried about and show methods of how to fix them utilizing their structure, which kind of comes along with additional logical stabilizers. Great. Any questions so far? Okay. So just to kind of hammer this point home, the ultimate goal of performing a fault-tolerant quantum computation is to reliably reproduce the joint logical measurement distribution of all of these measurements that we have using noisy components, right? So this is a classical output, and as long as the classical bit strings that we get out at the end are sampled from this ideal joint logical measurement distribution, then we can say that our computation was performed correctly. And so then in this sense, preparing the logical co-state is a means to an end. It's nice if we can prepare it, but it might also not be necessary for us to prepare that zero logical state. And to achieve this, of being able to look at the classical output without reasoning about the intermediate state, we have to think about the computation as a whole, right? If we slice it in the middle, then all of a sudden we need to reason about things that are halfway in between, which are still quantum states. And so we really need to analyze the fault tolerance and think about the computation as a whole. So to do this, we'll utilize a suite of tools that have been developed in the community in the last few years in a variety of very nice works, essentially thinking about the decoding problem or the error correction problem in space-time. So here we use the concept of the so-called decoding hypergraph, also known as a detector error model in the very nice implementation from Craig Gidney and Stint, where this hypergraph essentially encapsulates how errors lead to observed checks. So errors in this case are hyperedges, checks in this case are vertices of the graph. I'll give you a more specific example in a moment. And so the decoding problem is essentially trying to identify the most likely error that can lead to the checks that we observed. Just to give a very simple example with the repetition code, this is a classical code, but the same idea generalizes. So we have 3 bits, and then we check the Z1, Z2 parity or the Z2, Z3 parity of the neighbors. Then for the decoding graph, we'll associate checks as comparisons of syndromes at different rounds to see if they changed. If they changed, then we know that an error event may have occurred. And so essentially the errors trigger checks, and the checks are what we observe. So in this particular case, we have 2 stabilizers or syndromes that we form these checks on. And if there was a data qubit error on the first qubit, it will flip the first one. On the second qubit, it will flip both of them. And then the third qubit will be like this. If there are measurement errors, then when we compare consecutive rounds, we'll also see a difference. And so this allows us to have these time-like edges, and then we can continue and keep going in this. And so really, it's a very simple formulation for how errors in any location in space-time trigger checks in space-time. And it's essentially taking the standard formalisms of stabilizers and error correction and just phrasing the whole computation process in the same way in space-time. So a lot of prior work analyzed this in the context of space-time codes or space-time decoding. But here what we're going to do is to take the same idea and apply it directly to the whole algorithm. So in this case, we have our transversal gates, we have our stabilizer measurements, and we have some prior knowledge or prior model for what the different errors in our system can be. So then from this, one can very efficiently, because this is just Pauli's propagating through Clifford's, one can very efficiently calculate this decoding hypergraph and construct it. And essentially, here we're constructing the decoding hypergraph for the entire algorithm. We're no longer thinking about the individual pieces. We're just looking at the entire algorithm as a whole and applying this same space-time decoding idea. In this setting, then, the fact that we're using all of this information throughout allows us to use stabilizer information on one layer of time and in one logical qubit to help correct the other ones. More specifically, if we're working with a transversal Clifford circuit, as we'll mention, also suffices for the purposes of eventually going into the direction of universal quantum computation. If we're taking an adaptive Clifford circuit, then the gates that we need to propagate these errors through are all Clifford gates. And so we can try to use the surrounding stabilizers to help correct errors. And essentially, for any given error, you might imagine that there are actually a lot of neighbors that could help you to figure out whether there was a mistake and help you correct it. And so really the hope is that by looking at this whole thing together, errors in one location might trigger a bunch of stabilizers, but collectively you have enough information to figure out where an error was. And indeed, if we think about the number of locations, when we do a gate, there's maybe order the code patch size number of errors that are produced. And so there's kind of one time slice of errors that we're producing. So maybe having one time slice of syndrome information per error would actually give us already enough information or entropy to try to perform some of these corrections. I should mention that there's a lot of very nice complementary work in a variety of papers. Madelyn did some analysis earlier on this, both numerically and at a high level. And there's also very nice recent works looking at this in a variety of different settings. But most of them have so far been analyzing in the 1 to 2 C0 setting. And here we're interested in just directly applying this to the whole algorithm graph and seeing where we can get. So let's, with this in mind, go and think back about the state preparation question that we heard earlier.
Hi, there's a question. Do you want me
Yes.
to?
Yes,
so,
please.
So let me, Omid, you're allowed to talk now if you want to ask your question. You're muted.
Oh, I'm sorry. It was a mistake. I apologize.
Okay, no worries.
Okay, great.
You can continue. Thank you.
Okay. Yeah, so let's go back and revisit this question of state preparation and try to understand what where the challenges are and what might happen here in a more specific case. So for concreteness, I'm going to illustrate this in the surface code here, where you have these yellow plaquettes that are Z stabilizers, green plaquettes that are X stabilizers, and these circles that you see here are data qubits. And the logical operators run these directions as illustrated. So if we want to prepare the logical plus state, then what we can do is initialize all physical qubits in plus, measure the stabilizers d times if we want for it to be reliable, and then apply the corrections to bring it close to the ideal logical plus state. So what goes wrong if we only measure once? Well, if we measure once, then initially we initialize all of the physical qubits into plus. So all of these yellow plaquettes, these Z stabilizers, are completely random, right? We don't know what their values should be. And so when we perform this one round of stabilizer measurement, it may very well be that one of our stabilizers was measured incorrectly, but we didn't know whether it was measured incorrectly or whether it actually was flipped already in the first case because it was random. And indeed, one can show that with only order 1 rounds and applying these corrections to try to go back into the code space, the fact that you didn't know whether you made a mistake in the stabilizer measurement or whether the value truly was flipped actually causes the resulting state to be a mixture of product state that is not close to any logical code word. This is nicely summarized in this paper by Hastings, and also one of our panelists, Jeongwan, had a very nice talk giving more details about this. And so in other words, the single stabilizer measurement error intuitively might be causing a very high weight X error that causes us to not prepare the right state. And as we mentioned earlier on, incorrect measurements results could lead to a flip in our interpretation of the logical measurement result, thereby causing an incorrect feed forward. And it is precisely because of considerations like this that in the past, when people had looked at transversal gates, had looked at similar settings, for example, in these two papers, as well as many other works, typically it is assumed that the initialization and the measurement need to be separated by d rounds, so that by the time we reach the measurement, we gain enough confidence that we're really putting things into the right code space. And just in a little bit more detail in terms of what might happen. So, for example, initially with our limited syndrome information up to this first logical measurement, we may have chosen a correction that looks like this and pairs the stabilizer to the left boundary. But later on, upon more syndrome information, we might realize that actually the more likely thing that may have happened was, in fact, we paired to the right boundary for the correction. And this in total then would cause us to have an X logical error applied net between these two cases. And it might seem that this would then flip this logical measurement, and now we're all of a sudden applying an incorrect feed forward. But the key thing here is that there is actually structure to the logical difference between these two cases of we paired to the left or paired to the right. In particular, these two cases both need to cause you to be consistent with the stabilizer, with the checks that you observed. And because the total correction between them needs to commute with stabilizers, you actually know that it has to be on net a logical X operator that separates the two. So in other words, when we're trying to do this plus state preparation, there's a possibility of a logical X error that we're getting. But at the same time, this X error also comes with a logical stabilizer on this plus initial state, right? An X logical acting on a plus state leaves the quantum state invariant. So there might be a sense in which this isn't truly a logical error. It's making it complicated because in different rounds, we're going to interpret it differently. But at the same time, whenever there is a difference in interpretation from one round of decoding to another round of decoding, the difference is always this X Pauli error, which is exactly the same as the logical stabilizer that we have on this plus initial state. And so what we'll be seeing is how we can use this basic fact of the structure of this initialization error to show that, in fact, we can still consistently reproduce the whole measurement distribution, even given that at this particular point, we haven't fault-tolerantly prepared the state. In more detail, we want to show that this works for a universal quantum computation. And as has been shown in prior works, a universal quantum computation can be performed via adaptive Clifford circuits together with magic states for non-Cliffords. The adaptive Clifford circuits allow the possibility of measurements and then mid-circuit feed forward, which, for example, is useful to teleport in these so-called magic states, such as a T magic state that points halfway between the X and Y axis on the equator, which allows us to implement non-Clifford gates and achieve universality. These magic states can in turn be distilled from noisy magic states with Clifford gates. And so really, if we can reliably implement adaptive Clifford circuits with these mid-circuit measurement and feed forward, then we can use the same technique to do magic state distillation and thereby complete our whole computation. And indeed, this is the standard way that, for example, the surface code plus lattice surgery architecture does these things, where you're essentially doing a bunch of adaptive Clifford gates using lattice surgery. Now, another thing, just to remind you again, is that we only care about the joint logical measurement distribution of all of these measurements that we performed, and not on the individual quantum state intermediate. So we'll be focusing on whether at each step of the computation, we can correctly reproduce the distribution. So now in this setting, let's think about these Pauli initialization errors that we were worried about. So in this case, because we're going through an adaptive Clifford circuit, a logical Pauli operator will propagate through this circuit and become a product of Paulis. But notably, it's still a Pauli operator because it's going through a Clifford circuit. And so then when this Pauli operator reaches a measurement, there are two different cases. The first case is that this new measurement that we're performing commutes with all of our logical stabilizers. So for example, here, this initialization error propagates here, but it's a Z operator acting on a Z measurement, so it doesn't do anything, and therefore we get the same result. And so in this case, we see that the measurement basis is insensitive to the initialization errors, so we might expect that the usual fault tolerance arguments apply, and we get the correct result. In the other case, we might encounter a situation where instead we have a measurement that anti-commutes with one or more of these logical stabilizers or logical initialization errors. In this case, the result of this one measurement will actually be 50-50 random, because applying the logical stabilizer or this initialization error that we have flips the measurement, but these two things anti-commute, so essentially the result has to be 50-50 random, because applying the logical stabilizer shouldn't change the distribution of the result. And so this marginal distribution by itself is actually unaffected by initialization error, because if you flip it, it's still 50-50, so nothing really changed. However, we do need to ensure consistency with the prior measurements. Remember that we're trying to ensure the joint distribution and not just individually getting the right marginals. And so in this case, then, we need to do a little bit more work. So for example, if we had at time t1 some measurement here, and then later on we run some more measurements, then in this case, we need to ensure that when we do decoding of the new measurement with this new syndrome information, we're not changing our mind about what we assigned to earlier. And remember, this was the key challenge that we saw before, where with more information, we might realize that to do the decoding correctly, we should actually flip this measurement result, thereby causing an inconsistent feed-forward. Crucially, however, as we saw earlier on, these two different rounds of decoding, they have to differ by an initial Pauli error on this initialization state with high probability. And so we can actually apply a logical stabilizer that was here to correct this measurement that we had and committed to before and fix this inconsistency. And this, of course, because we want to apply the full logical stabilizer, we also need to apply the corresponding operator up here. So now our interpretation of this new measurement should also be updated so that we're doing it consistently with the old measurement. In other words, we're going down this branch of different measurements where we have this tree of different possibilities, and each time we commit ourselves to a given branch down the tree, the problem that we might have been concerned about is that given the new decoding information, we realized that we actually went down the wrong branch of the tree and ended up somewhere else very different. But it turns out that because of the structure of this initialization errors, actually there's always with high probability a logical stabilizer that you can apply that actually brings you back into the branch that you were in, while self-consistently reproducing the right distribution for this new measurement that you're trying to interpret. And indeed, we can prove that the probability that this type of consistency check fails, or that the consistency check fails, also decays exponentially in the code distance, using very similar techniques to how we can think about the fault tolerance in the usual setting. Essentially, the idea is that for two rounds to be inconsistent, or for a logical error to happen in general, you need to have an error chain that goes across the system, thereby having a size that is the same as your code distance, and which is exponentially unlikely. So maybe just to reiterate of what, in terms of very concrete practical terms in the procedure, what this would mean. We have some prior decoding rounds that we perform the measurements and the feed forward. We apply the feed forward based on this logical measurement and continue with the computation, this adaptive Clifford circuit that we're running, and then we run into these new measurements. With these new measurements, we need to perform decoding with all of the information that we have. But this decoding may cause some of our previous measurement results to now take on a value that is inconsistent with what it had before. However, we can restore this consistency by applying the appropriate logical stabilizers, which in the first place caused this inconsistent feed forward. And indeed, this is a very simple propagation of Pauli through Clifford circuits to determine which logical stabilizer flips what measurements. And so it's actually a very easy, efficient computation to do this inference of what we should apply. So we formally formalize this in a theorem in our paper, where we show that with these constant time order 1 round of syndrome extraction, we can actually perform transversal Clifford operations, including the state preparation that one might think was hard, and the feed forwards in constant time. And we've recently been extending these techniques to the case more detailed analysis of the state injection in magic state distillation, where we believe that the results still work, and we'll update our manuscript soon with these updated results. So just to summarize again the main ideas, we saw that...
Sorry, can I ask a quick question? Should
Yes.
I understand that at the beginning of the talk you said something about constant time, but then you also said that you also want to claim that the space-time overhead is constant, and I don't see that statement in the theorem.
Yeah, no, the statement isn't that the space-time overhead is constant, is that it's reduced. So for example, for the surface code, previously we would believe that it has d cubed space-time volume per operation. This reduces it to d squared, but it doesn't make it constant space-time. Yeah,
okay.
That's a good question. Great. So in the previous approaches, we would try to guarantee that things are individually fault-tolerant, whereas here we're really trying to guarantee that the whole algorithm, when you consider it as a whole, is fault-tolerant, and that we only guarantee the classical output instead of the quantum state. And this allows us to achieve this in order 1 rounds. Now, thinking a little bit more about the intuition, a large part of what we're using is also that we have these transversal logical operations that are directly doing the operations instead of going through intermediate rounds, intermediate unreliable stabilizers. And so the main role of syndrome extraction now is to remove entropy from the system instead of performing the computation. Because this is the case, then we might imagine that we remove entropy at the same rate as the generation, where there's order 1 rounds per gate instead of order d rounds, thereby allowing us to reduce the time overhead for the same thing. So essentially, we take the usual ways of doing surface code, and you can shave off the time direction by a factor of d, pretty much a drop-in replacement to the standard magic state distillation plus surface code schemes. So we've seen that this works. This seems to work in theory, but how well does it work in practice with circuit level simulations? So the first thing that we did was to perform a numerical simulation in which we performed decoding with only the syndrome information so far. So here we prepare 2 plus states and then repeatedly measure a ZZ operator between them. But each time when we interpret this measurement result, we only allow you to use the information that has been measured so far. In this case, using the techniques that we see here, we can see a very clear threshold behavior that is greater than 0.85%, which is close to the 1% threshold for the standard memory surface code in the same setting. Here we're using surface codes for each patch. And so we see that the threshold is actually quite close, and this might be expected because in 1 round of syndrome extraction, there are 4 C-naughts, while in a transversal gate, there's 1 C-naught. So there's actually fewer C-naughts in the gate, and therefore we're probably not adding in too much more noise when we're doing this. We're still adding in a little bit, which is why the threshold gets reduced, but it's maybe not too big. The second thing that we went and checked is that this 2-step decoding approach that I described, where we first do the usual thing and then apply these logical stabilizers to ensure consistency, we wanted to make sure that this indeed was necessary. And we indeed see that only with applying the second step do we see this nice exponential error suppression with code distance. And so this demonstrates that really this extra step that we're doing here is quite necessary to get the right results. Next, we compared the implementation of transversal gates with this order 1 round per operation with lattice surgery, where we also only give it order 1 rounds instead of d rounds. In this case, we see that the lattice surgery has an error rate that increases, whereas the transversal gate, even with just order 1 rounds, is still fault tolerant and shows exponential error suppression. And finally, we looked at a more intricate example, going towards something that would be relevant with these magic state distillation things that are necessary to achieve universality. So here what we looked at is a state distillation factory, which allows one to distill good resource states from noisy ones, and thereby completing universality if you distill T-gates. Here we're actually distilling what's called either the I state, Y state, or S state, which points along the Y-axis on the block sphere. It turns out to still be somewhat useful for the surface code, although better schemes exist. But the nice thing is that we can, because it's all Clifford, we can efficiently simulate it while still getting at many of the same pieces of state injection, of transversal gates with order 1 rounds, and actually also of doing multiple levels of this. So in this factory, post-selecting on certain logical measurement patterns, the output logical error rate is suppressed as p cubed. And we indeed see when we perform the numerical simulation that for a single level of this factory, if we have large enough code distance, then we indeed see this expected behavior. And moreover, we actually simulated up to 100 or so logical qubits with 2 rounds of distillation, where the first round output is put into a second round of a larger patch size. And we again see that the output infidelity follows what you would expect from the factory formula of this cubic suppression, indicating that indeed this circuit is correct and fault tolerant in these relatively complicated blocks. Now, for the T magic state factory, which is ultimately what one would be interested in, this actually has a very similar structure to the S factory, in which we have it's almost like 2 copies of it with a little bit more gates. So we do expect the conclusions to readily transfer. And with this, then one can complete the universal quantum computation by using this type of approach to prepare the magic states. So we've talked a little bit about the concrete numerics. And now let's think about if we wanted to implement it on an actual experimental quantum hardware, what the implications would be. So if we had a system that was wired up, then there might be an extra cost for reconfiguring the connectivity in the computation, because in order to do this, we're making use of these transversal gates where one logical qubit might talk to several different logical qubits throughout its lifetime. And so really, in addition to the typically quoted long-range connectivity requirement of counting resources, there's actually a very important aspect of reconfigurability also coming into play and allowing these types of schemes to be implemented here. There might be other ways that this can implement it, but the most natural one that one might think of seems to go this way. And so for atomic systems, such as neutral atoms or trapped ions, maybe even quantum dots with shuttling, you can imagine that they natively support arbitrary degree reconfiguration. And so you might have native transversal logic implementation that allows you to tap into these speed advantages coming from these fault tolerance approaches. Now, this is on the quantum hardware part, but also we need to think about how do we actually support the quantum hardware with classical decoding. And to some degree, we're reducing the quantum runtime, but possibly making the classical decoding problem more challenging. In particular, instead of very easily and trivially breaking the problem into independent pieces, now we need to think about a larger block directly. So there are fewer decoding problems, but each decoding problem is a lot larger. Note that the processing throughput that we need to deal with per syndrome round is actually still the same across the whole system. You still have this many logical qubits, and so the amount of syndrome throughput that is coming in and the amount of total processing power might actually still be on the same order of magnitude, but still it's a more complicated problem that we're dealing with. Now, if this classical decoding becomes too slow, then we might actually want to insert a few extra rounds to either simplify the decoding, break it up slightly smaller, or wait a little bit. But crucially, this construction still allows us to go below D rounds, even in that case, so that maybe we don't go all the way to 1 round, but we still can reduce the number of syndrome rounds compared to what one would have naively expected. Moreover, there are many different techniques that one might imagine of speeding this up. For example, you could try to utilize the algorithmic structure. In many relevant algorithms, such as this linear ripple carry adder, you might have a linear growth of the relevant decoding space. And so then you might imagine that the total decoding volume doesn't blow up too much. Moreover, you could try to utilize the structured error propagation in specific circuits to further improve the performance. At the same time, although our input wasn't decomposed into multiple blocks, it might be that because the error clustering, your decoding problem can naturally be decomposed into data level parallelizable blocks anyway. And moreover, we can try to reuse the previous decoding progress so that we're still making good use of the information and not having our decoding problem become too complex. And finally, as we also have experts on this on the panel today, there's also methods for hardware acceleration of the decoding problem. And so I think there are many exciting research questions and possible avenues for this decoding to be improved and to really hit and reach the requirements that we might need in practice for this scheme to work. So with that, I've told you about some of our work on transversal algorithmic fault tolerance, combining these different ideas of transversal logical gates, of doing correlated decoding and thinking about the fault tolerance of the whole algorithm, and finally, of coming up with new ways to identify the structure in these errors that we were worried about and allow us to nonetheless still implement things fault tolerantly, even in the presence of feed-forward. And with that, we see this factor of order D speedup that we elaborated on here. I think there are many exciting directions to think about in the future. We can think about, as I mentioned earlier, combining this with low space overhead schemes, such as these various quantum LDPC code constructions, both from our teams, as well as our collaborations, as well as many other nice works across many different groups across the world. We're excited in thinking more concretely about how to design a neutral atom system hardware architecture that enables this. And finally, as I mentioned already, fast decoder development will be a crucial area for really this scheme to come to fruition. So with that, I'd like to thank my collaborators, particularly Maddie and Chen, who were instrumental in the development of these correlated decoding and fault tolerance ideas. And thank you for your attention.
Great. Thank you, Harry. That was a fabulous talk. Before we go on to the panel, I'd like to see if there are any questions from the audience.
So we have one on the Q&A. Let me read it for you. Can you comment on what your results might indicate for schemes that perform logical gates on a single block of a QLDPC code?
Yeah, that's a great question. So if you directly take the single block and just do transversal gates on it, actually our proof already directly applies to that case. However, when you have a big block, these types of transversal gates commonly only give you a very small sliver of the whole set of groups, whole set of operations that you would want to do. And so then you might need to mix and match it with other things, and then the results wouldn't directly apply. So I think a lot more research is required to understand this. We have some ideas, but I think more work is needed to really flesh that out.
Thank you. Here's another one. It asks, what assumptions have you made in the proof for each one of the syndrome rounds?
Yeah, so I guess in the proof itself, in some sense, we assume that the amount of errors that come during each slice of time is fairly limited. For example, I think in the case that you're describing, where the measurement is super, super long and you might have a lot of idle errors during that, then you would need to be a little bit more careful. We use a single parameter P to bound all of the error rates in a given round. However, in that case, if you have, like, for example, multiple, say, atoms that you could bring in to do the measurement in subsequent rounds, then you could actually still do things in a way that catches errors. It's just that the scheme now has latencies that you need to worry about and treat them more carefully. Yeah.
Yuri, would you like to ask your question yourself?
Yeah, sure. And I'll ask two for the cost of one. First, a simple question. Harry, would you mind making your slides available? I to bring them up to my team here.
Yeah, I can certainly see if there's avenues that we can make it available through Simon's. Yes.
The
Would
recording of the
appreciate
talk will also be available on YouTube, by the way.
Yeah.
would appreciate it greatly, please. And second, do you think your results would be applicable to attacking lattice-based cryptographic systems, such as the latest NIST post-quantum crypto standards?
Yeah, so in this construction, essentially what we've done is taken the error correction fabric and reduced how big each block would need to be, essentially a drop-in replacement on top of what you would already be running for a usual quantum algorithm and reducing the space-time volume. But it doesn't change what algorithm you're trying to run. So I think there it maybe is a bit more of a question on the algorithmic side. How do you find an algorithm that maybe breaks some of these lattice-based crypto systems? I think this wouldn't directly change it. It would only, maybe if you had a scheme, make it a little bit cheaper to run.
Great.
Understand. So it doesn't offer a specific breakthrough against lattice-based crypto, but whatever system one or whatever algorithm one might have, it will improve it significantly.
Yes.
Yeah.
Appreciate
Craig, do you want to ask your question?
Yeah. So there are existing techniques that decouple the runtime from the code distance, even in lattice surgery. So specifically, Austin Fowler has a paper from, I think, 2011 called Time Optimal Quantum Computation.
Yeah.
And I was wondering how this technique compares to that, where that one, basically the clock speed, instead of being determined by the code distance, is determined by how long does it take the decoder to determine a measurement, and physically, how long does it take to do the measurement? Yeah.
So in that case, you're kind of snaking around and using bell pairs to connect things such that you can do a bunch of Cliffords in parallel. That's the scheme that you're, at least at a high level, talking about, right?
Yeah. It moves all of the operations on the hot path to become transversal X and Z basis measurement.
Yeah. So in that case, at least oftentimes when you look at the standard ones, you would use this spell trick to kind of bridge things together. And if you naively look at this, then there's a Bell state preparation followed by a Bell state measurement, which you might think has with this picture of, oh, I have an error from the initialization, required D rounds of separation in the analyses that have typically been done so far. And so then in that case, this part would still take a larger space-time volume to execute in the standard scheme compared to if you use this approach. That being said, if you do have a computation that is reaction limited, where you're just doing a chain of reaction limited operations, and the transversal and the operations otherwise are really quick, then the total amount of runtime may not be blocked by these Clifford operations, and so the amount of saving would need to be more carefully analyzed. Yeah, so I think that's a great question in terms of for a given case, if you're using the resources and you could, instead of idling, put them towards some of these types of approaches, how the overall space-time volume of the computation would get affected.
Yeah, it does seem like it would turn it into a space saving. You turn your work into a space savings instead of a time savings, and it might be useful to quantify the amount.
Yeah, that's a good idea.
Harry, could you stop sharing your slides so they can set up the panel?
Yeah.
Okay. Great.
I did have a question as well. Slides.
Yes.
We're not going to see them again.
Oh my goodness.
I can share briefly again if that's small.
Yeah, is that okay? Because otherwise I'm just going to
Sure.
have to go back to the slides. Okay.
Yeah.
Yeah, first, thanks for a great talk. I think it's a really important topic for people to work on. I think for far too long, people have been congregating at conferences around a coffee stall, pontificating on what the answer to this question would be instead of actually doing any work on it. So it's good to see some work happening on it. I read the main text of the paper, and I haven't got through all of the appendices. And so the place where me and some of my colleagues are at is that we don't quite understand why the theorem and the claims are fully true. We're trying to get the intuition from the main text. And so I'm just going to poke at some of the kind of intuition building examples that you've given in the presentation. So in particular, if we go back to slide 36, which is the same, I think, as what we got figure. Back one more, please. Okay. Yeah, maybe this is not the right. Yeah, so if I think about this circuit that you've got here, if I understand what you're saying, you do one decoding. The first step is just up to when the first measurement happens.
Yes.
And then you do a second decoding on the full circuit or when the next round of gates has happened. Yeah?
Yes.
There's a difference between like first step and second step. And the thing that enables you to do the second step is that some of the states are prepared in stabilizer states, and therefore you can add this extra frame operator, pull it through, and then change the outcomes of the measurements kind of post hoc in some sense. Is that correct?
Yes.
Okay. So my question is, what happens when I have a circuit where all of the initial states are non-stabilizer states? They're all T states. So the claim holds for all circuits, so it should hold for ones where there are no stabilizer states, but then I can't do this trick.
Yeah, so in that case, what happens is that the T state that you're preparing it with reliable stabilizers through this magic state distillation process. And so those actually already have valid stabilizers. And so we are already not worried about them causing these errors. Really, the key thing that...
Okay, but they only have valid stabilizers if they've been prepared for D rounds, yeah?
Which comes from the factory itself. So for the T states, the factories provide you with sufficient fault tolerance up to the distance parameter that you want there.
Okay, so first of all, that means that your space overhead is d cubed now, so the d squared claim is gone.
Yeah, I guess it depends a little bit on how you count this. The claim, for example, in the regular surface code case, right? When we say d cubed per operation, it's counting usually when people say that they mean the like say doing a gate, and also then for the factory you have these layers of different like you use a concatenated factory with different distances, and so then it's d to the gamma. So
it's true that people will often count resources per gate, but if we're working in a reduced form where we have a single T state for every T gate we wish to execute, then number of gates equals number of states, and the cost of each state is d cubed in space-time, so you're back to d cubed.
The cost of each one, so I think you would one would need to look a little bit more carefully at the costs within the distillation, right? Because you have the space costs of each patch, and then there's also the distillation exponent. So I guess I'm not necessarily sure whether it has to be d cubed given that. It can be less than d cubed potentially.
Okay, but that's probably worth checking before repeating the d cubed claim. Can we go to the next slide, please? Okay, so let's say that we have a circuit where there are only T gates and we're doing transversal C naughts and then making measurements. Because I don't have any stabilizer states anymore, I can't do the both steps thing. I can only do the first step. Oh, I know what you're going to say now. This made me worried because it looks like I have to have both steps and I can't have it when I've got magic state preparations. But your answer is going to be, because the magic states are reliably prepared, because I've allowed for d cubed space overhead possibly for them, I don't have to worry quite so much about doing both steps. That's what I'm guessing your answer is going to be.
Yeah, like essentially in that case, Yeah,
Pardon?
those two will be the same in that case. Yeah. And
Okay.
then when you do the actual decoding in practice, you still need to apply the same formalism into the factory. And so into
Yeah.
the factory, if you had like Pauli basis state preparations there, then which you may or you may not have to, but if you did have them there, then you would need to apply this technique. Yeah. So it's really, I view it, maybe the earlier d cubed versus d squared was a bit of a like too broad way of phrasing it. Really, the statement is compared to the standard approaches or assumptions that people often make, you
Yeah.
shave off the time axis by a factor of d. Yeah.
Okay. And then maybe one last question. So I don't know if you actually had this circuit. It was the one you had like a teleportation type circuit in your paper, figure 2. I don't know if that's in the slide deck as well. But I don't know, it kind of comes maybe a little bit to the question that Craig was asking about the time optimal approach. So in the time optimal approach, you're very much limited by the response time or the reaction time of having made a measurement. Yeah.
Yeah.
So in this two-stage decoding approach, you say you do one stage, you decode, and then you do classical feedback based on that, and then you correct what happened in the first time in the second step, which kind of makes the first step look redundant. Why do you even need to do the first step? And if you don't even need to do the first step, why don't you just pick the measurement outcome to be whatever you want and then fix it later? In which case, I kind of almost have a paradox that you can go infinitely fast and maybe even you can just decode afterwards.
Yeah.
So
Yeah, that's a great question.
so if I can phrase that as a question,
Yeah.
what's going on with the first step, second step? Like, why is the first step even necessary if you're just going to change it with the second step?
Yeah. So so I think maybe the specific example that we had in the paper, we're also planning to update, and that maybe kind of led a little bit down this direction. But essentially what's happening here is that you have these initial states these Pauli initial states here, and each of them have logical stabilizers. And for some of these later measurements, you can apply a logical stabilizer that flips many of these in a correlated way. And so for some of them, you might indeed think of them as almost like computationally agnostic, in the sense that you didn't actually need to decode them you could just flip a coin and it's still 50-50 for these first ones that appear. And so actually there's only a subset of them that you actually, for example, in this magic state factory, only for a subset that have non-trivial correlations left do you need to actually do decoding. Yeah. Does that answer the question?
Yeah, I think that it does, but yes, I'm going to come back to it. Thank you.
Thank you.
Okay, great. Well, let's move on to the panel then. Let me introduce the panelists. Earl Campbell, who we've heard from already, he's a VP of quantum science at Riverlane, and also on leave from or associated with the University of Sheffield. How would you say it? Either one? Okay. And he's obviously an expert on fault-tolerant quantum computing. And okay, so Maddie Cain, who is co-author with Harry, is a sixth-year PhD student in theoretical physics at Harvard, working in Misha Lukin's group, and she works very much on resource-efficient, fault-tolerant compilations of useful quantum algorithms, and collaborates very closely with the experimental work in neutral atom arrays. And last we have Jeongwan Haah, who recently moved from Microsoft Research to Stanford University. And Jeongwan, you probably know, is of Haah code fame, which also, of course, led to the discovery of new phase of matter called fractons. So really great to have all of you on the panel. It would be let's start with a few minutes from each of the panelists. If you can talk to the theoretical significance of this work, and as well as prospects for implementation, and any other historical comments. In any order. Earl, if you wish to continue to speak, then
Maybe someone else
can
should have
go
a
around.
turn. Come back to me.
Okay.
Well, do you hear me?
Yes,
Yeah.
John.
Yes, well, this is certainly very interesting. There is a conceptual. Actually, still, I have a barrier to understand this claim and all the arguments around it. The context is from the more of a physics side. I usually think of, well, okay, so here's a mathematical fact that Harry also mentioned during the talk. If you start with the product state and then start measuring the stabilizer, but you stop the measurement at some overrun round, say you just did it once, then the underlying state is far from the anycode state, but more close to the completely, well, not completely, but more closer to the product state or separable state. You have to make it precise, the closeness. So if you if all the measurement steps are of order 1, starting with the product state, then you are effectively working with the very high temperature state of the 2D toric code or surface code. So it sounds like at the very high level that this claim that you could do the fault-tolerant computation using all 1 rounds is conceptually more akin to saying that you can do fault tolerance using arbitrary high temperature state rather than approaching a 0 temperature where the quantum effect must be more pronounced. So in that aspect, there is a conceptual well, for me, a barrier to believe in this result and then trying to understand the proof more deeply. And so,
sorry, John. Can you repeat the argument? I didn't completely follow that.
No, it's not an argument. It's just a mental analogy. Okay, why do we need error correcting code in the first place? We need to encode information in some entanglement pattern of the underlying many qubits. And in terms of more physical, intuitive picture is that probably you want to approach the ground state where the entanglement structure is more important, and the code space of the surface code is the 0 temperature subspace of that local Hamiltonian. And that has you could interpret the error patterns you can try to interpret the error patterns in the presence of some thermal noise or local noise as some stat max situation, and you can make an analogy of the error contaminated states used to the thermal state. And you can make it precise in the sense that starting with the product state, if you measure just once, then then such a state is trace distance close to the high temperature Gibbs state of the toric code. Well, high temperature Gibbs state of some classical Hamiltonian. It just and then of course that's different from saying that you could do some operationally meaningful task or not. That's two separate questions. But I have believe, and I always thought that the repeated measurements amounts to the cooling process that brings the whole system from the high temperature state down to very low. And of course, here very low doesn't mean 0, but the D rounds of error correction amounts to the temperature of order 1/D. And that is sufficient to suppress all the quote unquote thermal errors. And that has been one of the reasons I didn't even doubt that you must need a D rounds of error correction. Now this result says otherwise. So I'm still on the conversation with Harry about the scope of this. And at some point, well, to be honest, I wanted to disprove that this could ever work. I mean, did I say right? I wanted to prove that this should not work. But formulating that question mathematically, I again hitting a roadblock. How can I prove that a certain scheme does not work? Well, to begin that question mathematically, I should start with some criteria for the fault tolerance. And this is an operational thing, at least. In the worst case, if you make a surface code of distance, say 3, and then you make a measurement just once, and for some small error probability, that logical qubit is a pretty bad, but not too bad, a qubit. So you could, in principle, bring another error correcting code at the logical level and do all the things you wanted, and you still achieve a formal sense fault tolerance. So the best thing I could do then is to come up with some definition or criteria that what does it mean to have a fault tolerance using surface code? But that alone, I don't know how to make that precise. For example, the magic state is, well, I mean, okay, here's a way to get around. So get around my conundrum. The archive version, I'm not sure if it's updated for the last month or so, but the original version had the assumption in the theorem that you should be provided with the perfect T state followed by some local noise channel. And all the Clifford states, I mean, the Pauli stabilizer state could be prepared using the stated scheme, the preparation of the product state, and then some small number of rounds of measurements, and then do the correlated decoding. But once you assume that you're provided with a perfect T state, that sounds like you're only correcting the Clifford errors, where we didn't even need error correction in the first place. So then the question becomes, how can we prepare this perfect T state? Well, one way is to go to higher dimension, where the T states are transversal and then map it back to the 2 dimensions, say. But then we are momentarily, in some sense, outside our scheme to our promise that we are only going to use the surface code. Well, I mean, it's not. Like I said before, I wanted to have a criteria or a situation where that my follow-up scheme only uses surface code scheme, but that's not a very well-defined notion. So operationally, I should allow using some other codes momentarily. And for that purpose, you could go to some other crazier code or better code. And perhaps the distillation procedure that Harry was mentioning was functioning of that sort. I'm not sure. So my current understanding is still, I'm in a very curious stage. I would like to see the update.
Should I add comment?
Yeah, please do.
Yeah. No, I think these are all like kind of really important intuitions that also helped us formulate a little bit what was interesting about the aspects of our work. So maybe first, several things just to again go along the directions that you just described. First, indeed, a large part of how you are actually able to do the full computation is exactly coming from the fact that you're doing, in this case, the magic state distillation, and the magic state distillation boosts your distance to be D for the T states, essentially. Mm-hmm. So that part is definitely true. And then now the question is, like, if we think about the usual way that we're doing the computation, using these surface code plus magic state distillation approaches, where does the runtime enter into there? And compared to those approaches, can we actually get a reduction? And there then, a lot of times, at least as far as we've seen in the literature, this fact that want to fault tolerantly prepare a state that is the zero logical state already gives you d rounds and already pushes your logical time up to something that is at least d rounds or order d rounds. And so what this achieves is a reduction of these components from order d rounds to order 1 rounds. But it is indeed the fact that those, like when you prepare a logical Pauli state, the information there is in some sense still in like a classically tractable state.
Mhm.
So you don't have to prepare that into a quantum state that has like fault distance d there yet. And it's only when it interacts with the rest of the computation with these t states that were prepared with the d rounds that you now need to like now when you measure, you get the right results because you're doing kind of this, you're keeping track of that classical information as well, and you're interpreting it accordingly and consistently. Yeah. So indeed, I think as you said, there's the aspect of do we need all of our quantum code states to have this low temperature aspect throughout the computation? And here, what we show is that the answer is no. If you consider everything together, the Pauli states here do not need to have that aspect of very low temperature. But the reason that they don't have to have that aspect of very low temperature is because they are classical pieces of information in the first place. And the true resource that is allowing you to do the universal quantum computation is in some sense these T states. And for those, you still need to go through the distillation procedure, and the distillation procedure provides you with enough reliability on that piece of information.
Yeah, but this was the point that I was picking up on, because then it's a question of how do you compile your algorithm to see if you get any improvement? Because if I compile my algorithm in such a way that I remove all of the stabilizer states, which I can always do, yeah, you're going to end up in a situation where you just have T states, C naught gates, maybe some Hadamards and measurements, right? And then it's not clear what I've gained.
Maybe one quick comment, at least as far as I'm familiar with this approach of recompiling out the T states, recompiling into just initial T's and then Pauli product measurements. In that case, at least when I've looked closely at the construction, you actually still rely on doing the measurement non-destructively, and then you have a qubit that you then get to continue to use. So you have n qubits coming in, you have the T states, so they're all T states, and then you do some measurements. But then in the process of doing this, you're actually doing a measurement such that it's like a non-destructive product, which if you actually were to implement it, you can't directly measure that without an ancilla. At least that's to the extent that I'm familiar with the papers.
That's like the more recent kind of like Pauli-based computation model that came from some of Sergey and others' papers. But if you go back to like the old graph state models where you think of preparing a graph state, the textbook way you would explain it is you prepare a graph state, which is a bunch of plus states and CZ gates done between them. And then you make measurements in bases that are kind of non-Pauli bases. But you can always rewrite that. You can kind of take a T gate that's on the measurement, pull it through and put it on the state, and change it to a problem where you've got a bunch of T states. You do CZ gates, and then you make single qubit Pauli measurements in one of two bases. And some of these have dependencies on each other in such a way that like another one depends on the classical output of another one. And then they're all single qubit measurements, right? So in that picture, which is the one that I often kind of mentally have in my head, having been of the graph state quantum computing generation, in that picture, all my T states have to be prepared using distillation routines that are reliable. And then I know that, they can't be the starting point of any of these bad kind of like trains of strings of measurement errors that go upwards. And so they can't be any strings that change the values of the outcomes of the measurements that you're performing that you're conditioning feed forward on.
Yeah, I would need to look into and better understand the details of the scheme to understand why it does not require any non-destructiveness or otherwise. But in that setting, yeah, in that setting, then one would still need this aspect of correlated decoding throughout in order to get the gains. And that I would say actually has, I guess that one is maybe a little bit more folklore believable, but also hasn't been spelled out or done very carefully before. But then in that case, relative to that, the gain would be more limited. I think there's a big gain compared to the standard. Oh, maybe when I say standard, there's like a set of things that people typically have been doing in a lot of the estimates, in a lot of the more recent resource estimates. There is a reduction compared to that. For example, in this Beveland et al. Paper that I cited, and some other related papers, including those that have looked at doing transversal gates, but have highlighted the possible need for a fault-tolerant state preparation. So relative to those, this scheme does achieve a reduction, but I would need to better understand the details of the graph state scheme that you just described. Yeah.
Okay.
Maddie, would you have any comment?
Well, I guess I can comment just to add to what Harry just said. I think that we are relying on gaining distance from the factory itself, but relative to kind of the standard way that people typically think of also doing magic state distillation, saving a factor of d in time there is also quite nice.
Yeah.
I guess adding kind of thinking more broadly about the implications of this work, I wanted to add a few more comments to what's already been said. So I think that although the proof techniques in order to get this result are somewhat complex, the key physics that's enabling this result is actually quite simple, which is that when we're doing transversal algorithms, kind of the sole purpose of stabilizer measurements is to remove entropy from the logical qubit and just track physical error accumulation over time. So it's not doing any damage to the encoded logical information. It's quite benign. And so this is, in contrast to stabilizer measurements really being a requirement for a logical operation to happen, like you would need in lattice surgery. And so because syndrome extraction is now really a tool to track errors, I think that it's exciting to think about how it can be optimized and tailored to the circuit and the algorithm that you want to run itself. So like one interesting case where this might arise, for example, in circuits like distillation, where you might originally think of needing a depth of order D in order to kind of concatenate your surface code into something larger. All of a sudden now the depth is very shallow. And this means that you can get away with very little syndrome extraction in practice, only doing enough to kind of track which errors have accumulated before you do that final transversal measurement, which in my mind, kind of going back to what Jeongwan was saying, like the transversal measurement, because it's so reliable, it almost takes us from a very high temperature state to a very low temperature state, because we really gain reliable syndrome information when that happens. So I think that that idea of kind of co-designing and optimizing syndrome extraction and the algorithm itself, coupled with, we have experts here on the decoding side as well, thinking about how that'll interact with the decoders is actually quite interesting. And I think that there will be a lot of progress made on this in the future. And I guess the last thing I would say is that I think it's likely that we can probably even further prune the overhead of error correction by taking this idea that Harry talked about, where really all we're trying to do is reproduce our kind of classical measurement distribution of our logical outcomes, and really kind of further pruning unnecessary elements of the circuit itself that don't help us preserve this kind of core information. So yeah, that's what I would kind of add.
Great, thanks. Earl, you almost feel like you look like you want to say something, but
Yeah, well, I certainly agree that this this aspect that the transversal gates is helping us in terms of error correction should be exploited for much more than previously done. I did some resource estimation myself some time ago, and my working was, well, there are many unknowns, so the error bar is pretty large. And so at that point, I thought there is no point of optimizing everything because the other error bars are too large to wash out some small improvements I might have. So the convenient assumption was that, okay, every operation you should do the most conservative thing possible. And then we could go down we could reduce the runtime, but well, let's give a somewhat baseline. That's my intention, and probably in the existing report, similar assumption may have been made.
Yeah, so I think I agree broadly that there's going to be some massive savings from using transversal logic in neutral atoms, ion trap type systems. And I think you highlighted a 10x to 100x saving that's going to come from replacing order D with order 1 in terms of, let's say, the amount of time it takes to do a T-gate by teleportation. In fact, it could be bigger than that in a sense, because if you look at something like the kind of classic picture of how you would do things in a rigid 2D architecture with superconducting qubits, you've got a factor D overhead that comes from the time it takes to teleport in at a T-gate, but also you have a whole lot of routing overheads that's there. So much so that people often find it easier just to say, look, I'm going to do one T-gate at a time, just because the routing is too complicated. Now, maybe that's just, overestimating the cost of doing things in rigid 2D, but that's what people often do. And that probably, for a large algorithm, you could probably be doing 10 T-gates in parallel. There'd probably be nothing to stop you from doing that. And so it's possible that the gain is even bigger than 10x. But that also is really, really important because, as you highlighted at the beginning of the talk, the runtime for a neutral atom type platform, if you are forced to put this extra cost on top of the fact that the gates are over 100 times slower than in superconducting, would really kill you. So absolutely everything to do with getting transversal logic working is completely essential for neutral atoms to be competitive with fast qubit types like superconducting qubits. So I completely agree with the importance, and I love seeing the simulations. I still have my mental block on the fine details in the appendices, which I need to resolve. That's probably me not having enough time to spend reading papers as I would like. Yeah, I guess the one thing I'd maybe bring it back to, and it's the paper I probably need to go back and think about again, is the one that Craig mentioned about Austin's time optimal approach. So, like, if we say the claim is the time to execute a T-gate is order 1 per T-gate, and there's some, order D cubed space-time cost, but we're not worrying about that, then there's a risk it starts looking similar to the result that Craig was talking about, because in there they show that you can do things in a way that's only limited by the reaction time, assuming that you've prepared some state that has a cost that is like order D cubed, right? So if we're just talking about big O claims, there is a risk that the old Austin Fowler paper plus lattice surgery has similar big O results, but my expectation is that in practical numbers, it would still be several orders of magnitude more expensive.
Great. Craig, you had a comment, I think. Do you want to say what you meant?
Oh, I was just riffing off of what Earl said. He said he referred to this Latinsky paper, which allocates an entire hallway across the entire computation, and then every T-gate uses the entire hallway. And this is very inefficient compared to what's possible, but it's also very straightforward, so you don't have to think about it. And
Great.
this has made it somewhat popular in a frustrating way.
Oh, Misha is here. Misha, you had something to say?
Yeah, so yeah, I just wanted a quick comment. So I really enjoyed this discussion. And I guess maybe there are two kind of points here, as everyone kind of articulated already. One, of course, is I mean, it's clear it's super important. And I think what's also like this kind of teaches us is that in terms of really looking at a, let's say, logical clock, the speed of the clock really should be looked, for this kind of like system as a whole, right? The fact that if one certain, type is slow, right? If for example, if transversal gate is relatively slow, by gaining, like extra fault tolerance, you can more than compensate this slowness. And I think things like this are absolutely critical for us, both for us, but for entire field to, to succeed in the next few years, so. And I mean, the second, on the flip side, maybe on a kind of very general kind of, a point that Jeongwan started with. So I think we might really need to rethink a little bit, what makes actually quantum error correction so powerful, because it does feel indeed somewhat non-intuitive that you start with the state which has kind of high temperature, but what is it like? What is this temperature even defined with respect to? So I guess, in some way, like, in a kind of, in the surface code, right? So if you make a measurement, your sort of energy scales are kind of infinite anyway, right? So, and, internally we are kind of, as Madi indicated, we're starting to think what really matters is entropy extraction. So it does not matter what is like kind of initially your defect density, but if you do the gates, you really have to and you add the entropy, you really need some way to actually get this entropy out, and maybe that's really the key thing, which our correction, has to do, and everything else is secondary. But I think these are really fantastic, questions which are worth exploring, so.
Yeah. Thanks, Misha. Greg, you had something to say again?
I had one way that you could frame this work, I think, is we like to draw 3D space-time diagrams of lattice surgery, where you end up with this big construct of tubes and junctions. And all of the operations in this system correspond to basically 2D planes, like 2D cuts of the tubes that are different. So, connecting two tubes that are next to each other is just a relatively small change. That's a 2D squared area. In the normal layout where you don't have, where you have planar connectivity, these planes are always separated from each other. So these D squared regions where you're making changes can't be too close because you can't get enough logical qubits into that region fast enough for that to matter. And so you might end up thinking, it's not just that I physically can't get them close, but there's actually some error correction reason that I don't want them close. Like I can't correct it fast enough. So one way that you could frame this paper is showing if you can get a lot of logical qubits close very quickly, these 2D regions can stack close to each other and it still works. So the density of operations can go way up compared to what is normally present. That's it. That's all I wanted to say.
Great. Dominique?
Hey, yeah, I don't think I have anything to add right now.
Okay. Oh, you have your hand raised. Okay, sorry.
Oh, sorry.
Yeah. Great. We are probably close to the end of the panel. If there are any further comments by any of the panelists. Oh, maybe John Presko. John, would you like to speak?
Yeah, I wanted to come back to this issue of the trade-off between reducing the quantum depth and increasing the complexity of the decoding. Now, my naive expectation might have been that, yeah, we can reduce the quantum depth to, the number of repetitions of the syndrome extraction to order 1 instead of order D. But then to do correlated decoding, I'd have to track error propagation over many rounds of syndrome extraction. So potentially the classical cost of doing the decoding could grow exponentially with distance if I still have to track, for a number of rounds that scales with D. But now the errors are, proliferating or exponentially. The number of logical blocks affected could make the decoding very hard. So, I mean, do you have in mind like changing the architecture so I don't have to worry about that? Like, I don't keep logical qubits alive for so long that I have to track for so many rounds? Or what are your thoughts about that?
Yeah, that's a great question. Maybe I'll first give my perspective, and then I'd also be very curious from the other panelists. Like I think Earl probably will have more thoughts on this, for example. I guess there are two aspects that make the decoding more challenging. One is the fact that you have a larger decoding volume now, potentially, as you mentioned. The other is that it's now, in some sense, intrinsically a hypergraph decoding problem. The hypergraph decoding problem, one hope would be that a lot of the existing methods, like hypergraph union find augmented with BP, can still give you at least reasonable practical performance, although that, of course, still needs to be further developed. Maybe the bigger problem, and the earlier one, just to mention, hopefully still in at least polynomial time. The bigger problem potentially is this increase in decoding volume. And for that, I think actually it precisely gives us a new different design consideration for the algorithms, as you mentioned, where you want to control the decoding volume to not increase too much. And in certain algorithmic gadgets, maybe they naturally give you that. As a very simple example, as I showed in the ripple carry adder, at least if you do it in the direct way, as shown, although I think if you use these bell pair tricks to bend it around, because it's connected in that fashion, you still end up with a similar result. There, the growth of the volume is scaling linearly with the depth. So if you go back D rounds, then you involve order D qubits as well. And so then the growth of this volume is somewhat bounded to be linearly growing with the distance D. This is one important aspect to it. And then the second important aspect, I think, is that when we're doing this decoding, even though when we put it into when we phrase the problem itself, it's potentially a larger problem, and it's not obvious how to, at the input level, separate it into multiple smaller decoding tasks. With this intuition that we often have in error correction, where the errors are actually clustered, I think there is still the possibility, although it obviously requires both empirical and theoretical investigation, that the errors actually naturally form small clusters in typical instances, such that when you decode, you don't have to go and explore this entire potentially exponentially large, or maybe linearly large decoding volume. You just need to work with a decoding volume that is actually set by the error cluster size. And then hopefully, in that regime, you would still get reasonably good performance with a relatively fast runtime. I think for classical, this isn't an exact analogy, but for example, you may hope that there are techniques that allow you to parallelize it such that you get, say, like log D parallelized depth. At least I'm not aware of arguments that prohibit that, but of course, doing that in practice would still require further development. I think some of these ideas that were developed in the past in the literature in terms of parallelizing these based on these clusters may still give us reasonable performance in practice. Yeah.
Yeah, it's not clear how much we should think about it as a very local problem versus a very large sprawling problem, right? Because if you assign detectors in the right way, then you still have an error kind of triggers a local cluster of detectors. But you don't have this problem that it stops being QLDPC in some sense. But you do have the consequences of an individual error can propagate off to exponentially many patches as a function of the depth, as John noted. So yeah, I think this and related works is going to start motivating people to think about decoding in a different way, to really think about how can we make large correlated decoders more scalable. And maybe, there's this kind of culture at the moment where there's one extreme, which is everything is one massive correlated hypergraph. And then this other extreme where you say, oh, I'm going to look at every surface code patch and try and treat it independently. And though those aren't the only two options. There are other options, and I think we're going to see some interesting work over the next few years that kind of tries to divide it up a little bit, but keeps enough of the correlated properties that you can still get some of this performance. Yeah. I mean, yeah. It's still interesting to ask what can be done even if we assume that decoders are infinitely fast, because that gives you, a first step into the theory of what's going on. Then you ask what happens when we add a finite reaction time on. And that's one of the things that I have a mental block on with understanding at the moment in the work. So like, if I'll just come back to this 1.1 more time to illustrate, it's the thing I need to go away and think about. It's that when you have the first stage and the second stage, you do the classically controlled Clifford off the first stage, even though it's unreliable. And then you fix it up later with the second stage, which makes it reliable. But if it's the second stage that makes it reliable, and that's left a long time till later, that's almost like saying that I can just do the classical feedback operation to do that Clifford, conditioned off the Pauli measurement, arbitrarily, and just fix it up later anyway, which is extremely counter to all of my intuitions. So that's one of the things that I'm really stuck on with trying to understand.
Yeah, maybe just to comment very briefly on that, it's that for some subset of measurements that had this they were in some sense computationally agnostic to start with because of the logical stabilizers in the system. For those, you can actually just choose to not do the feed forward even, and it would still be correct.
Yes. You gave this example of the 15 qubit read monocode, and I was trying to remember why 10 was a special number out of 15. I think it's that there's 14 stabilizers, 4 of them are Z-type, the other 10 are X-type. Exactly. So there's only one class of them that you're actually correcting. You actually have to do feed forward on.
That's correct. Yeah.
Good. Any last comments?
I have one question. Well, thanks a lot for the great talk, Harry, and great panel. My question is related to Jeongwan's intuition relating the D with inverse temperature. Do you think that intuition is still valid for the case where temperature is not homogeneously defined, like sort of a deep state, you may have a non-homogeneous distribution. Do you think that intuition is still valid? I guess that analogy between the D and inverse temperature that you mentioned.
Could I answer, or Jeongwan, do you want to?
I was going to ask, was the question directed to me or to Harry?
Well, I guess that was the intuition that you brought up, Jeongwan, but I'm happy to hear anyone's.
Well, I'm still in the curious mode. Yeah, it is conceivable. Well, I mean, most of the Clifford operation, you don't ever need any entanglement. You could, well, for example, in a dumb, very silly way, that you just repeat your Clifford measurement many times and then pick the majority, and you could reproduce, for example, the barrel correlation in that way. You don't need to measure any stabilizer in that, for example. So the temperature analogy just plainly fails in that case to produce the Bell correlation classical outcome. On the other hand, yes, there's a conceptual barrier. Yeah, I'm not totally sure. Could it be that? Well, I'm just saying it loud. Could it be that the cooling, effective cooling effect on the T factory is enough, cold enough to absorb all the heat from the other components? Yeah.
Yeah, I guess I would maybe still argue that the heat on those other components is not relevant to the classical output of the computation. Because and I guess maybe another part of the intuition that Maddie mentioned, and I didn't highlight as much in my talk, but I think is also quite important, is when we do these transversal measurements, we're getting reliable information on those logical qubits. And so for the basis that you actually cared about, you do get in some sense a set of perfect stabilizers to work with. That's just inherently built into the transversal measurement. So even though if you looked at the intermediate quantum state at a given point, you didn't yet cool it down. In some sense, by the time you need to interpret the logical measurement result, that aspect is irrelevant to the interpretation. Yeah.
Okay, so on that note, let's bring this to an end. Next week we won't have a quantum colloquium because we have a workshop at Simon's on quantum algorithms for open quantum systems. So please, I think that's going to be streamed too. So please attend that if you are interested. Thanks, Harry, again for a fantastic talk. It was very stimulating. And thanks to all the panelists, Jeongwan, Maddie, Earl. That was really, really great discussion. And of course, thanks to all the people in the audience and those who participated in the discussion, especially. So see you in 2 weeks.
Thank you.
Great.
Thank you again, Umesh.
Oh yeah, thanks. That was really nice.
Thank you.